Well, hello again. Welcome to the VK60S Fun with Amateur Radio channel. Bit extra gurgly today, but I'll try and keep talking. Now, first a warning. You might, on this video, you might catch a glimpse of my knees. There we go. But relax. I am wearing shorts, so you won't be getting any nightmares. Now, someone said, left a comment saying that they thought that the loading capacitor would probably be okay because they're, the tune and load capacitors are huge. Now, they are huge because of the voltage rating, the spacing between the plates. So it doesn't necessarily mean they are of a high value. Now, 2000 picofarads would be good for the load, and I couldn't remember what value this capacitor was because I bought these capacitors years ago, back in the 80s. They're made by Capco, so if anyone knows what the values of the Capco capacitors were that were produced back then, you could let me know maybe what it's supposed to be. Now, there's a bit of padding across the load capacitors. I think I showed you the other day, the four doorknobs. They're 47 picofarad each, and four of those in parallel should give me 188 picofarads. Now, if I take this off of here, a pretty awkward position actually, leaning over this thing, but I'll give it a crack. There we go. And then go to the capacitance meter. This is a Ultronics capacitance meter. That's showing 213 picofarads. So probably got about 33 picofarads worth of stray capacitance in there, give or take, depending on the tolerance of the 47 puff capacitors. Okay. But 30 picofarads on a big loading capacitor like that really is neither here nor there. Right. Okay, so let's get that off of there. Put that on there. Excuse me. Okay, so now it's on the load capacitor. And I'll zoom that in there. There we go. You can see it's 1,289 puff. Now, I would say, because it's possible that I've got 30 picofarads worth of stray capacitance there, it's probably supposed to be 1250 at a guess, that big load capacitor. And if I swing it around, I'm just adjusting the knob on the load capacitor there. 290 is about the most it will go to. And as I continue swinging it around, obviously as it becomes unmeshed, the capacitance decreases. There you go. Capacitance is coming right down. I've got a feeling I might have done this before, I'll have to have a look through the old videos and see if I actually measured this capacitor. So 80 picofarads looks to be about the minimum. No, still going, 76. So it's possible it's supposed to be sort of 50 puff minimum, maybe. And as you can see down there, it's fully unmeshed. That is now fully unmeshed. Camera down in there. It's not going to focus, is it? There we go. It's fully unmeshed. That's the load capacitor down the bottom there. So the actual capacitance is a bit on the low side for the lower frequencies as a load capacitor. Now, our VK6 KOF said to me the other day, why don't you, if you think you don't have enough L or you don't have enough C, why don't you just use a higher frequency band? And I thought, up there for thinking, down there for dancing, Al. Why don't I try it on 40 meters? So maybe I'll be doing that, but I don't want it to run on 80, of course, and I would like it to run on 160 as well. Now, so the load capacitor needs padding, and it's going to need a bit more than the 188 picofarads I've got across it. So if we say it's what, I don't know, 1250. So 12, so that's 12, 13, 14, you know, it's still about, I think it's still about 500 picofarads shy of an optimum value of load capacitance for about 80 metres, I think, with this type of amplifier. It's going to depend a bit, of course, on the tank circuit. Now, I do have another tank coil. There we go. Now this one here has got a tap. It's got a tap on every turn. Look at that. That is absolutely perfect for getting it sorted out for all the different bands. And I would say, looking at that, it's got a bit more inductance than I've got there at the moment. But this is a capacitance, that thing there is a capacitance inductance meter, so I'll measure the inductance of the existing coil here with the extra bit on it. And I'll see what tap corresponds to that. I might have to put a couple of extra turns on here, maybe. Now, the other thing that all this depends on too is the HT voltage, because the valve draws, you know, different amounts of anode current with different amounts of anode voltage, and you can, as a ballpark figure, you can calculate the anode load resistance by a simple calculation. I think it's the voltage, the anode voltage divided by 1.6 times the anode current. So what I need to do is get the HT rail to be what it's going to be, rather than all this right up in the sky or way down below stuff that I'm getting with this transformer at the moment. See what sort of current the valve draws, and then calculate the anode load resistance, and then calculate the value of the components that should be in the tank circuit, and then I'll see how far short the load capacitor is of the required capacitance, if it's short at all. Now, I also have another transformer to try. This one here, fairly nice big toroidal transformer, and this should give me, with no load on it at all, this should give me about 4,000 volts. Now, I've got no idea what it's going to sag down to. It's pretty substantial transformer, so I wouldn't expect it to be too saggy, but then it's going to have a voltage doubler on it, so I don't know. If it sags down to 3.2, 3.3 kV or more, I reckon that'll be perfect. And from once I know what that HT value is, I set up the idling current to be the appropriate level. I then look at the anode current it's drawing. Then I can do a ballpark calculation with regard to the tank components and see how it all looks. All right. Well, as always, I hope you found that interesting. And oh, that is scary, isn't it? You'd never pick that I'm a POM, would you? As always, thanks for watching. I'll catch you next time.